Hello, welcome to this video. This is 2B-4 and we are going to talk about logarithms. We are going to first learn about what a logarithm is and how to evaluate it, and you'll be successful if you can write a logarithm as a power expression, as its inverse. You know the terms to describe the parts of a logarithm. We'll get into that, and again, you can evaluate a logarithm. So we're going to start out with where logarithms come from, and that is this idea of powers. And so we have powers of 2 and 3 here, and we're just going to go ahead and evaluate these expressions. So I'll start in the middle at 2 to the power of 0. 2 to the power of 0 is 1, and we know that 2 to the first is 2. 2 squared, that's 4, and 2 cubed is 8. Well, what about negative exponents? Remember, the negative exponent property says we take the reciprocal and we turn the exponent positive, so this is going to be 1 over 2. 2 to the negative second, well, that's 1 over 2 squared, which is 1 over 4. And 2 to the negative third, well, that's going to be 1 over 8, 1 over 2 to the power of 3. And so I kind of want you to see kind of a connection and a pattern here with these exponents and their negative counterparts. So we have the same idea here with base 3. We can do the same thing. 3 to the power of 0 is 1. 3 to the first, 3. 3 squared, 9. 3 cubed, 27. And then we can go and look at the negative exponents as well. We have 3 to the first, which is 1 over 3. 3 to the negative second, 1 over 3 squared, which is 1/9. And then we have 3 to the negative third, which is 1 over 3 to the power of 3, which is 1 over 27. So kind of keep that in mind as we go ahead and jump into this lesson. In the previous lesson, we learned that for an invertible function, inputs and outputs switch to create the inverse function. And we also learned that the graph of a function and its inverse are reflections over the line y equals x, this identity function. In this lesson, we're going to learn about the inverse of an exponential function, which is called a logarithmic function, and also a logarithm. So let's go ahead and let's look here at graphing f of x equals 2 to the power of x. And so all I'm going to do is I'm just going to evaluate 2 to the power of x, and we've already done this. Negative 2 gives us 2 to the negative second, that's 1 over 4. Negative 1 gives us 2 to the negative first, that's 1 over 2. 0 gives us 1. 1 gives us 2. 2 gives us 4, and 3 gives us 8. And so I can go ahead and I can plot these here on my graph. So if I plug in 0, I get 1. 1 gives me 2. 2 gives me 4, and 3 gives me 8. Okay, and then for the negative values, again, we have 1/2, and then a quarter, and then I guess an eighth. But here is an exponential function. This is base 2. So y equals 2 to the power of x, an exponential function. And we went ahead and we talked about this identity function. The identity function is the line y equals x. It has a slope of 1, and it's just a line where all of the x and y values are exactly the same. So here's my line, y equals x. And what we want to go ahead and do here is we want to graph the inverse, f inverse. So all I'm going to do is I'm going to go ahead and switch these values, okay? And so you can look at it, you can make a table here, or we can just go ahead and kind of calculate these values. So 1/4 gives me negative 2. So 1/4 gives me negative 2. 1/2 gives me negative 1. Okay, 1 gives me 0. So all I'm doing, right, is I'm switching my x and my y values. So 2 is going to give me 1, 4 is going to give me 2, and then 8 is going to give me 3. Okay, and so this graph, it's going to be a reflection across this line, y equals x. Okay, and there is a logarithm. So this is the inverse. This is the inverse, f inverse of x, which is a logarithm. And this is actually what we call log base 2. And so the base has to deal with whatever base inverse it is. So since this was 2 to the x, this is log base 2. Okay? So, recall, inputs and outputs of a function switch for its inverse. For 2 to the power of 3 equals 8, the input is 3. I have 3 as an input, so what I plug in and what I get out is 8. The inverse would be log base 2 of 8. Log base 2 of 8, and the output is 3. So now my input is 8, and my output is 3. Log base 2 of 8 equals 3 also means that the base of 2 must be multiplied by itself 3 times to equal 8. Okay? So when you're looking at this, right? So when you're looking at this, you have to go ahead and kind of think about, okay, what power am I going to raise this logarithm to give me this value? So for instance here, I'll just give you another quick example. If I had log base 3 of 9, well, 3 to what power gives you 9? That answer is 2. Okay, and so that's a logarithm. So really quick, let's just kind of solidify this idea of switching inputs and outputs. Here I have an exponential form, and they want us to go ahead and complete the exponential form and then write the logarithmic form. So 2 to the 4th, that is 16. And what I'm going to do is I'm going to write this as a logarithm. So a logarithm is just simply written as log. The base is subscript, so it's going to be a small number below the g. Okay, so log base 2, and then inputs and outputs switch. Logarithms have parentheses, almost like trigonometric functions, sine, cosine, tangent, where you plug something in, a quantity in. So we have log base 2 of 16, and what we get out is 4. Okay, so this output is going to be an exponent, or it's going to be a power. Okay, so here is a practice problem. Please go ahead, evaluate this exponential form, make an answer, and then write it in logarithmic form. Okay, hopefully you went ahead and did that. Here you would get 1/9. So that means here log base 3 of 1/9. Well, what power am I going to have to raise 3 to get 1/9? -2. Okay, so that is logarithmic form. Hopefully in 2 you could just switch, right? Switch your input and output. Okay, that's a logarithm. It's the inverse of an exponential function. Do you know what a logarithm is? The inverse of an exponential. Good. So let's go ahead and again, let's look at exponential form. Exponential form, we have a base, okay, and we get a power, and then we get an output, okay? For a logarithm, the base is exactly the same. So they both have that base, log base b, but now that output, that was a power, that output, that's what we call the input, which is known as an argument. So here, A is called the argument, what you plug in. And for a logarithm, it's very important to note that A must be greater than 0, okay? Now, the input for an exponential function, right, this exponent, this is now the output. So n is the exponent, okay? And so notice that logarithms are equal to an exponent value, okay? All right. Other things to note too about the base, we talked about this with exponentials. Your base has to be positive, okay? If you're a function and your base is not positive, you're multiplying by negative, you alternate. You get an alternating sequence. Can't be a function. And then 2, your base can't be 1, because if you just multiply by 1 over and over and over again, you just get 1, and that's no fun. All right, definition of a logarithm. A logarithm is a mathematical operation to determine how many times a certain number, the base, is multiplied by itself to reach another number, which is the argument. Okay, and a fun fact, the term logarithm was coined by Scottish mathematician John Napier from, I guess he died in 1617, 6-7. Hey, it's 2025, so 6-7's the thing. In the 17th century, it's derived from the Greek words meaning ratio number. Pretty cool. Okay, So enough of me yapping. Here is the practice problem. I want you guys to go ahead and evaluate these exponential forms and then put them into logarithmic form. Okay? I'll go ahead and allow you to pause me here, and then I'll show you the answers to these. Okay, here are the completed exponential forms. 6 to the first is 6, 8 squared 64, 5 cubed 125, and 4 to the negative second is 1/16. And then in logarithmic form, we just switch our inputs and our outputs. So notice the base stays exactly the same. Log base 6, log base 5, log base 8, log base 4, and then our inputs and outputs switch. Okay, and so hopefully too you kind of thought about this like, hey, what's log base 5 of 125? Well, that's 5 to the third. So the answer is 3, okay? So we're going to do some more of that here, and let's look. Maybe that'll be better for you. Let's go ahead and look at these examples. These are all log base 3, just to give you kind of an idea of where they would be on this number line. And we want to evaluate. So log base 3 of 3, that is 1. That is 1. So here's A. Log base 3 of 9, okay, that's 2, so that's going to be B. Log base 3 of 1/3, well, that's 3 to the negative first, so that's going to be -1, so here's C. D, log base 3 of 1, man, 3 to what power gives me 1? 0. And you're like, hey, that's true for anything. Anything to the power of 0 gives me 1. Well, this is what we call an identity. So log base B of whatever that base is of 1 is going to give you 0. And then E, log base 3 of 1/9 is -2. So -2 is E, and that was D. Okay? All right. So here is a practice problem. Please go ahead and try these. Again, if you get confused, what you can do, you can always rewrite these, right? So 3 to what power gives me 1/3, right? So you can do that. Or like this one, 3 to what power gives me 9. Okay, and you can go ahead and answer that. All right, so pause me. Please try these ones. All right, here are the solutions. Log base 4 of 1 is 0, because 4 to the power of 0 gives you 1. Log base 4 1/4, that's -1. Log base 4 of 64, this is probably the most challenging one. We get 3. Log base 4 of 4 equals 1. Here's another important identity. Any logarithmic base of the argument that's the same as the base is always going to return 1. Right, because 4 to the power 1 or 5 to the power 1 would be 5. And then here, the last one gives you -2. Okay, and those are the values on the number line. So let's get kind of unique here, and let's throw in some different forms here. They say rewrite each expression in exponential form. This is just getting you comfortable with the transition between a logarithmic form and an exponential. So looking at this, what you first need to see is the logarithmic base. This is base 4, so I call it log base 4, and then 8 here, this is your input. This is my input, so that means it's going to be the output. It's going to be equal to 8, and then since this is my output in logarithmic form, it's going to be the input for my exponential base. 4 to the power of D is going to equal 8, okay? All right, pause me here and write this next practice problem, this logarithm in exponential form. Go for it. Is that what you got? Cool. Easy peasy. Okay, here are some evaluation. This is evaluation practice. And I'll just go ahead, I'll show you the first one, kind of what we're doing here, but you're just going to simplify. So feel free to pause me on these. But what we get here, log base 2 of 64, well, that's 6, divided by log base 3 of 9, well, that's 3 to the power of 2, gives me 9, so 6 over 2, our answer here is 3, okay? So, again, please feel free to pause me and try these, but then I'm gonna talk through these, okay? All right. Log base 3 of 81, that is 3 to the 4th. And I only know that because 9 times 9 is 81, right? That's 3 squared times 3 squared. That one would have been tough. So 4 to the power of 2, right? We have 2 on the outside. Answer, 16. Log base 5 of 1, 0. Anything to the power of 0 gives you 1. Okay, log base 5 of 1/5. Easy peasies. -1. Okay, so those are the first 4 here. So double check. 3, 16, 0, -1. And then let's go ahead and evaluate these here. So 5 times log base 4 of 164. This is going to be equal to 5 times, and I believe that would be negative 3, right? Because 4 to the power of -3 would equal 1 over 4 cubed, which is 1 over 64. So final answer here, -15. -15. Log base 10 of 10, hey, that's 1. 10 to the first power gives you 10. So here we have 1 plus 5. Answer 6. Okay. Log base 6 of 36. I know that one. That's 2. Log base 2 of 1/8. That's -3. So answer here is -6. Okay, and then log base 7 of 1 over 49, and this is going to give us -2. Okay, so hopefully, hey, logarithms, not too bad if you think about them from the frame set of a exponential function. All right, here is a context question about where you can see logarithms, and they want you to evaluate. So a population of deer in a certain area can be modeled by the expression 113 plus 8 log base 5 of 40t plus 5, where t is the years since the population has been monitored. Determine the deer population for time t equals 3. So they want this function evaluated at 3. Do you think you can go ahead and evaluate this? Pause me, see if you get the same answer as I do. Okay, so I'm just plugging in 3, and that looks like this is going to give me, what, 120? Plus 5 gives me 125, which makes sense because it's base 5, so that's going to be 3. So we get 113 plus 8 times 3, which is 113 plus 24. And that's going to give us 137. Okay, and because this is in context to, like, what is this 137? Well, it's 100. It's the deer population. So the deer population is 137. Specifically at t equals 3 years since they were starting to be monitored. Okay. All right, last kind of idea to think about, kind of develop some number sense about logarithms. These are kind of fun questions here, is determine which 2 consecutive integers the value of log base 2 of 7 is between. So if I have a number line here and I have 0, 1, 2, 3, 4, 5, 6, 7, where is log base 2, 7? Where would that fit here on a number line? And so rather than racking your brain and be like, 2 to what power gives me 7, think about it in terms of whole numbers. Like 2 to the first, that's 2. 2 to the second, that is 4. 2 to the power of 3, that is 8. So doesn't 7 live right here? Right here. So what that means is it means that log base 2 of 7, right, is going to live between log base 2 of 4 and log base 2 of 8, right? So it would be right between them, and so these values are 2 and 3. So 2 is less than log base 2 of 7, which is less than 3. So between 2 and 3 is where this number would live, right? If the output was 8, it'd be 3. If the argument was 8, the output would be 3. If the argument was 4, the output would be 2. So it lives between 2 and 3. All right, go ahead. Please try this for log base 3 of 40. Which two consecutive integers is this value between? Go ahead and try it. Okay, so you got to go to like powers of 3 that you know, and I know that 40 is between 27, right? This output is 3, and it's between 81, which this output is 4. That's 3 to the power of 4. So the answer is between 3 and 4. So 3 is less than log base 3 of 40, which is less than 4. So between 3 and 4. All right. Okay, final key takeaways summarizing what we talked about. We introduced a logarithm. This is the inverse of an exponential. And so we have some identities or properties, of course, that are developed. For any valid base, b of 1 is going to be equal to 0. We talked about this. If I have any base and the argument is 1, that's because the power was 0. So b to the power of 0 gives me 1. That's always true. Doesn't matter what b is. Okay, as long as it's positive and not 1. 2, for any valid base b, log base b of b is equal to 1, because b to the power of 1 gives me b. Which of the following can be negative? Can an argument be negative? No. Can a base be negative? No. Can an exponent be negative? Yes. You can have a negative exponent. Which of the following can't be 1? The argument can be 1. We talked about that, right? That this is a property. The base cannot be 1. Nope. But an exponent can also be 1. That's also another property here. All right, number 5. Which of the following cannot be 0? That would be the base for sure. Our argument also cannot be 0. Argument can't be 0. It has to be positive. Okay? And then the exponent can be 0. So cannot be 0. The argument and the base. Yes. Stop overthinking it. Okay, that's going to do it for this video on logarithms. Hope you liked it. Hope you learned something. Give me a thumbs up. Catch you next video. See ya.